Good afternoon. Today we are presenting our case study on the Ieee 14 bus power system covering power flow analysis, fault analysis, and transient stability. I'm Sun Yong Yi. My match number is 222963. I will be joined by my group mate Gan Li Yang. His match number is 225538. So let's get started. Okay, our presentation today is split into two parts. I will cover the chapter 1 to 3, which is the system overview, network modeling, and power flow results and simulation. So Liang will take over the chapter 4 and also chapter 5, so which cover fault analysis and transient stability. Let's start with the system overview. The IEEE 14 bus system is a standard benchmark network in power system engineering. It's a simplified approximation of portion of American electric power system. It's widely used across both academia and industry to test the power flow algorithm and also the control strategies. As shown here, the network has 14 buses, 20 transmission branches, and 11 customer load and 5 synchronous machine, which two synchronous generator and three synchronous condenser. Every value in our analysis is expressed in per unit normalized against a common 100 mega VA system base, which keeps the map consistent across the network regardless of the actual voltage level at each buses. Interestingly, because this network scale normally as well as dramatically, some research has even built small hardware version of it in the lab to validate the real-time behavior. But for this case study, we work entirely with the computational model. Our line transformer and generator data are sourced from Monitaba Hydro International PS card technical documentation and the standard IEEE 14 bus benchmark dataset. The full reference list is on our final slide. To run the power flow calculation, the 14 bus are classified into three types. The type 1 is bus 1. We know it is a slack bus. Its voltage magnitude and the angle are fixed at the 1.06 per unit and also 0 degrees. And it acts as the reference for the entire grid, balancing out the system real reactive power losses that we can't know in advance. Buses 2, 3, 6, and 8 are generator, or we call it as PV buses. They inject a scheduled amount of active power while holding a voltage constant, and their reactive power output adjusts dynamically within upper and lower limit to maintain that voltage. The remaining nine buses, the remaining nine buses, which include bus 4, bus 5, 7, and 9 through the 14, are the load buses, or we call it as PQ buses, with no local generation. They simply represent fixed active and reactive power demand, acting as negative power injection in the calculation. As you can see in the table, our system actually consists of 20 branches model as the standard pi equivalent circuit. To eliminate the calculation errors across different voltage levels, all parameters are normalized to 100 mega VA. Most of these are standard transmission lines. For example, the line from bus 1 to bus 2 has a resistance of 0.1938 and also a resistance of 0.05917, as you can see in the table. However, three specific branches, for example, the 4 to 7, 4 to 9, and also 5 to 6, act as the transformers with off nominal taps. These taps are critical as they let us dynamically step the voltage up or down to manage reactive power flow across the network. Okay, let me introduce you to some basic concept when we do the network analysis. So you can see all these branches parameters we just discussed are combined to build our 14 by 14 bus admittance matrix. We also call it as Y bus. Building this matrix is essentially a careful bookkeeping exercise. The off-diagonal terms represent the mutual admittance between the connected buses, while the diagonal terms sum up everything physically connected to a single bus. Once populated, this bus Y bus metric become a mathematical foundation for everything that follows, both the power flow results I will show you next and also Liang fault analysis later in the presentation. Okay, just now we just discussed how to build the Y bus, and now the next step to do is solve the unknown voltages at every buses. And to do that, we use the Newton-Raphson method. It is the industry standard for this kind of problem because Newton-Raphson is so fast. It has the properties of quadratic convergence and a strong numerical precision compared to alternative iterative techniques. And you can see on the right on the screen our simulation converge in just three iteration. The maximum power mismatch, that is the gap uh, between the power and the network, should be able to supply and what it is actually solving for, drop from initial 0.92 per unit down to initially essentially 5.9 times 10 to the minus 8. By the third step, that rapid clean conversion is a good sign. It confirms our Y bus metric and also bus data were set up correctly before we even look at the result. Here is the result of the powerful analysis. As you can see on the voltage profile chart, every single bus safely within the 0.95 to 1.1 per unit range. This confirms that we have a healthy, stable, steady state system. We also calculated the total active power loss to be 13.39 megawatts and identifying the line from the bus 1 to bus 2 as our busiest path, carrying about 157 megawatts. This result gives us a solid verifying baseline with this normal operating condition established. I will now hand it over to Liang, who will walk us through what happens in the network is disturbed by a fault.
Okay, so thanks Yong-Yi. So far we have looked at the system under normal condition. Now the question is, what happens when this network is distracted by a fault, and does it recover? A fault is any abnormal condition that breaks balance three-phase operation, usually caused by things like insulation, breakdown, lighting, or equipment failure. There are four standard types. The three-phase fault, LLL, is the latest, only about 5% of real faults, but is the most severe, so it is treated as the design benchmark for stability studies. On the other hand, single line to ground faults, LG, make up 70 to 80% of real world faults, but they are the least severe. LLG and LL fault in between. Our fault analysis track three states. First, the pre-fault state. This is just our chapter 3 base case. Second, the fault on state, where we modify the law and column of Y bus at the founder bus to drive its voltage toward zero. And third, the post-fault state. After the faulted line is isolated and the network is rebuilt. In all three states, each generator is represented by its transient reactance in series with a constant internal voltage source. That's the standard assumption for this kind of study. We tested two fault locations to see whether electrical distance from generation actually matters. Case A is a fault near bus 2, right next to a generator with relative small inertia. Case B is near bus 10 on the loop side, far from any generator. Both are bolted three-phase fault. Clear after 200 milliseconds. The only difference is location. The result confirmed our hypothesis. Case A produced a fault current of 7.08 kiloamps, and while the case B only reached 1.7 kiloamps, that's about 4.2 times smaller. This makes sense. The fault current is determined by the impedance path back to the nearest generator, and bus 10 is electrically much further away. We also look at what happens to bus voltage during the fault. At the faulted bus itself, voltage collapsed close to zero. Neighboring buses start too, but less severely the future they are electrical from fault. And overall, case B's voltage stay noticeably higher across the network than the case A. Again, because it is future from generation. Beyond three-phase faults, we also check asymmetrically faults, line to ground, line to line, and double line to ground. Since this actually make up most real fault, testing at three representing buses, the current magnitude ranking was consistent every time. Three phase is the highest, then double line to ground, then line to line, and then single line to ground is lowest. And again, buses closest to generation always show higher fault current. Okay, so
Now,
now
the dynamic
for the
questions,
dynamic question,
does the system
does the
actually
system
recover
actually
after the fault
recover
is clear?
after the fault is
This
clean?
governed by the swing
This
equation,
governed by the
which
swing
describe
equation,
how
which
each
describe
generator
how
rotor
each
angle changes
generator's
over
rotor
time
angle
based on the
changes over
imbalance
time
between the
based on
mechanical
the
and
imbalance
electrical power.
between mechanical
For the bus
and
2
electrical
generator
power.
specifically,
For the bus
our
2
smaller
generator,
inertial machine, a
specifically,
nearby fault
our smaller
sharply cut
inertial
its
machine,
electrical
a
output,
nearby fault
creating
sharply
an
cuts
accelerating
its
imbalance.
electrical output,
Whether the rotor
creating an
angle
oscillating
settles into a
imbalance,
stable oscillation
whether the
or keeps
rotor
growing
angle
until the
settles
generator
into a
loses
stable oscillation or keeps
synchronism
growing
depends
until the
entirely
generator
on
loses
how fast the
synchronism
fault is clear.
depends on entirely
Now,
on
the dynamic
how
questions,
fast the fault
does
is
the
clear.
system actually recover after?
That leads to the critical clearing time or CCT, the maximum time a fault can remain before at least one machine lost synchronism. For our bus 2 case, we calculated a CCT of about 826 milliseconds, which is in the same order of magnitude as the roughly 500 milliseconds reported in prior literature for the same fault location. The blotter patterns hold too. Lines close to a generator need much faster clearing than line future out on the periphery of the network. So how would a real operator actually see this happening in this time to add? That's where wide area measurement system come in. Using phasor measurement units or PMU to give near real-time visibility of the network. Based on the prior work on this same system, 3 PMU placed at bus 2, 6, and 9 give the base coverage. And notably, that include bus 2, exactly the generator we identified as having the shortest CCT margin. To summarize, our 40 by 40 Y bus model encore every part of this study. The Newton-Rapham power flow converged cleanly, with all voltage within limits and total losses of 30.39 megawatts. Fault severity turned out to be governed almost entirely by electrical distance from generation, and critical clearing time analysis showed that the protection and monitoring system need to be prioritized, allow low inertia generator buses, where the stability margin is thickest. Okay, so before the end, here is the full list of our data source and reference. Our network data comes from Manitoba Hydro International's technical documentation and the standard IEEE 40 bus benchmark dataset. And our fault and stability methodology draws on published study, including Lambo and Mola, and so on, all listed here and in our Lighten report.
That will be the end of our presentation. Once again, thank you for listening to us.